I'd like to give a little bit more on meshes. That we talk sort of about meshes. They may not seem to fit in here, but I felt we do a lot with meshes, and I needed to expand a little more on what we did earlier. So let me give you some techniques that we use with meshes, and I think it'll open up some possibilities for projects and for other things to try and in displaying of meshes. Uh, Polygonal meshes are pretty much the standard way for looking at surfaces, so it's worth spending some time to see how we can display them, or underlying that, how we can organize them more efficiently. Uh, and in particular, we're interested in polygonal meshes, which are usually used to approximate curved surfaces, or and they'll be produced typically in a standard CAD package that you design some sort of a surface, and out what comes is a lot of polygons arranged in a mesh. There are also a number of techniques that we'll hopefully have time to look at the end of the course, where you start with a surface, or you start with a rough mesh, and you do subdivision to get a much finer mesh, and that generates obviously a lot more polygons. Now, commonly, partly because of the how graphic systems work, we're going to mostly be interested in quadrilateral and triangular meshes. Obviously, if you have a quadrilateral mesh, knowing that each of those quadrilaterals can be converted into two triangles, they're effectively the same. But more important is that underlying being able to generate meshes efficiently and represent them and store them and display them, we want to really use triangle strips and triangle fans, so that instead of looking at each triangle in the mesh independently, that we can look at the mesh as being one or more triangle strips, and so that essentially every vertex after the first two creates a new triangle, which means that you have about a third of the storage that you would have had if you had dealt with each triangle independently. So let me look at how meshes arrive in a very natural way, and that's what are called 2.5 dimensional surfaces, where they're not as general as an arbitrary 3 dimensional surface, but they have the property that given two values, you always know the third, and typically because they're used in topography, we'll assume that y is the up direction and x and z are the two other directions. And you can think of x and z as being directions, say, on the surface of the Earth, and y is the height above the Earth. And so for every point on the surface, you go straight up from this little approximating flat quadrilateral up to a point. You only get one point. That's why it's not a general 3 dimensional surface, which could fold over itself and give multiple values for y, or potentially give you no values for y. You go up and you get exactly one value on that surface, which would, the simple examples I'll show you would be the height of that surface. And now if I rule this underlying x and z polygon or rectangle into n by m little boxes, then each of those, at each corner, I have a value, or better yet, I could say that the value at the lower left corner or the value at the center corresponds to a height up here, which has a value. In other words, I get an n by m matrix that has the values, and this is a very nice, simple representation of that surface. But then when I want to display it, I'm going to take those values and know that I'm stepping through this matrix that corresponding to equal steps in z and x, and I could take values, or I can say here's a matrix of height data for a region, and I construct little quadrilaterals by taking the corner points, or taking four adjacent points from the data set and constructing a 3 dimensional little rectangle in space that has those 4 points as its vertices. In other words, I'd have each data point would be xyz, where y was the height, and that determines a little polygon out in space. So now how do I display that? Well, one way to display it is for each, say, each line in the going across here, I display all of those heights by giving you by using the heights that are in those that are in the array, and I could do them in the x direction, I could do them in the y direction, or I can make little loops by using 4 of them. But here's one way. Here's some data that I've made. It's on the website. I use it a lot for assignments. Here's some data from Honolulu area, and it's I have some other examples looked at from a different perspective. But out here is the ocean, and the harbor is over here, and here's the mountains behind Honolulu, and little valley where the freeway runs up. Here it's displayed by just for the consecutive data points going across. For each row, I construct a line strip, and then I do it again going in the other direction for each column, and each column determines a line strip, and the y value is giving me the height. So it's pretty simple to display this as x's and y's, either as strip, 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 or as line loop, line loop, line loop, if you want to make little quadrilaterals out of adjacent points. One of the things you might notice here is that you can see through in various places because I haven't done any hidden surface removal. This one isn't too bad. I'll show you one that's worse in a little while. But if you don't do hidden surface removal, or actually hidden line removal here, you get into problems because for example, over here where there's a little crest, you could potentially see things on the other side coming through here, and you don't want to have that. So even though you might like having this grid displayed, there's a hidden surface, hidden line aspect to doing this well, and that's what we're going to be talking about in a minute. Just for historical reasons, I want to mention something called Plot3D, because even when I was doing 3D graphics here, there were a lot of people who were still using this thing called Plot3D, which was a standard Fortran graphics thing that had been around for probably since the early 70s. And what it did was use a 2D method because there were no 3D graphics systems around at that time. And the argument went sort of like this. Let me come back over here. It said, look, if I take a line going across, okay, go across in a given direction, I could think of that as comprising a surface, or actually a flat polygon. If this is x going in this direction, for x equals a constant, I could think for this value of z, I have these data values, and they could form the top of some sort of polygon where the sides go straight down, the bottom is flat, and the top of it is composed of all of these data points along that line of constant x. And if I think of it as being solid, there's a solid 2D thing. And so I could look at all of these data as being a sequence of these kind of polygonal objects where they're on 3 sides they're flat, and on the top they show the contour along that value of z. Now, if I want to display them and I don't have a 3D graphics system, then I could do something very, very simple, at least conceptually, where I could say, okay, if you start with the first one, okay, so let's say I'm going to do this front to back where we assume our viewer is this way. So I take the first one and I display it, and I say, well, first one just gets displayed as a solid polygon, and if it has any shape, then I see the shape from the surface from the top over here. Then I take the second one and I say, okay, the second one is behind it, but parts of it might pop up over the top. See, that's a little more clear in the middle where I look at these. Well, that pops over the top, but it can also go below that solid. So if I keep track at any time of where the present top and the present bottom are, as I add a new one, I can compute purely in 2 dimensions which little line segments, or actually parts of line segments, are going to be visible over the top and visible underneath, and I update my present top and present bottom until at the end you wind up with a plot that looks very much like this, all done in 2D going front to back. A lot of little intersections have to be computed along the way, and if you look at the code is really long. So when I used to work some summers out at Sandia, there were just people doing these all day long. They'd have these old Tektronix displays, and they'd be generating these kind of Fortran plots because the old Tektronix machines were standard. They plugged into standard computers, but the language they used was Fortran to do this. And so they ran this big program to do this. If you do it in 3D and say, no, these are 3D points, and I have a 3D system, and I'm going to make a bunch of little quadrilaterals or whatever, it's a trivial program. It's just, you know, a handful of lines of code to do this because you have an underlying 3D system that's going to do this. Okay, so let's go back here. So here's another plot. This is a very useful function for fun function to display. Goes by various names. Mathematically, it's the sinc function, SINC, which is sine of pi r over pi r, and it has some very interesting properties. For every integer value of r, it goes to 0 because the sign is 0. It's a little bit troublesome at 0 because the top is 0 and the bottom is 0, so you get a 0 over 0 form. But if you use L'Hopital's rule and take derivative of the top and the derivative of the bottom, you can show that it's 1 for r equals 0. So here's a function that starts off at 1, goes down to 0 at r equals 1, then goes negative, then comes back up, but it's smaller because you're dividing by r, and it goes like this. If you look at any cut through it anyway, here's the cut goes to 1 around, it goes to 0 around here, then gets negative, then comes back up, then gets negative, and goes on like this. It arises in a number of ways. In particular, if you look at when we get to talking about discrete systems and sampling theory, this arises in all of the underlying mathematics for doing sampling and reconstruction, which are going to be important. But here, we're just using it as a nice little, easy to generate, three-dimensional, actually 2.5-dimensional function, because you notice if I go up from the bottom, if this is the y direction, for every x and z, there's exactly one y. And because of its shape, a lot of people call it the sombrero function or the Mexican hat function. But what I want to look at is just how we display it. So in this display here, what I've done is display it just by drawing the lines of constant x and lines of constant z, and they cross. Now notice how complicated it gets in this area. Why? Because of the folds. You're seeing there's no hidden anything going on here. So all the things behind what's in front are visible going through here, and notice how complicated it gets over here. Up in the top, up here in the central lobe, you're seeing not only what goes on in the front, which I think are these guys here, you're seeing ones behind it. So even though it's kind of pretty, it's not what we really want. So how can we get a display that doesn't show things that are behind other things, or a slightly different way of saying it is back-facing parts of it. You know, we don't want to see anything that's facing towards the back. I only want to see things that are facing front. So one way to say is, well, what you need is you need polygons, you need them filled, you need triangles filled to display this in a better way. But what if I still want to see the grid? So one way to do this would be to say, okay, if I just want to see this shape, and especially if I'm doing some terrain problem where I want it to look real, then I could use 4 adjacent points to form a quadrilateral, then take the 2 triangles that I can break the quadrilateral into, and then use lighting and shading like we will be talking about in starting next couple of lectures, and display it with shading and lighting, and it'll look kind of real. But what if I want to see the grid? Well, now I don't want to go back to what I just had, so let me argue this. What if for each little quadrilateral that I formed as here, 4 adjacent points, what I'm going to do is display it twice. First, I'm going to fill it as 2 white triangles. Okay, so behind it, there's going to be a white triangle. I take 2 renderings, and then I do a black line loop using the same 4 points that go on top of it. Okay, so everything is going to be blocked by the filled polygons. Everything I don't want to see is going to be blocked by the filled polygons, and then on top of them, because I render, at least in principle, I think that if I render it second, it's going to on the edges color over the white with the black that I want for the line loop. Okay, well, let's see what happens, and here's what I get by doing that, which looks in some ways a lot better because you're not seeing through all of these lobes, and you're seeing here you're only seeing front faces here, the nearest faces. So this is looking a lot better, but notice how the grid has gotten broken up compared to the previous grid. Well, why is that? The problem is that even though I draw the lines over the filled triangles, there's little numerical errors going on in the rendering. Primarily in the GPU, in the rasterizer, it's not the mathematics is not perfect, and trying to put numbers exactly or two fragments exactly on top of each other so that the second one will get rendered second gives you this kind of display that breaks up all over the place. So OpenGL, and this got carried into WebGL, has a very nice way of getting around that, which is called polygon offset. So even though this is just making the point that even though we drew the filled polygons first, these errors, little numerical errors, cause problems. Okay, so polygon offset, what it does, it can be applied to lines, it could be applied to points, it could be applied to polygons. I'm going to apply it to polygons, and what it's going to do is move each of the fragments corresponding to a filled polygon, a displayed fragment from that polygon, a little bit away from the camera. And I set it up, and this is in the notes, by two parameters, and it may take a little fooling around with the parameters because the parameters depend on the slope of the fragment. If you think of the fragment as being a little polygon, its slope and a little bit on the implementation. But I gave you the values I give you are probably okay. And if I apply it now to when I render these triangles, it's pushing the triangles slightly back as they're being rendered. So now when I draw sorry for another little glitch. Now when I draw the polygons first and the lines second, the polygons are a little bit behind the lines, and it should display nicely, and in fact it does. So here's it displayed. I think this is a really beautiful display of it, and this is two renderings, one for each little quadrilateral, but it looks beautiful on here. White polygons with black line strips on top. So it's a technique you probably want to use fairly often. So let me just summarize finally, and then I'll show you a display. Oh, let me show you the display first. Let's look at the display. So here we go. Okay, here's the hat function. It's on the website. It's just called hat. It's under chapter 5, and I've got some buttons here. Probably should have replaced these by sliders. But here's the hat. Instead of using white polygons, I'm using red polygons, and you can rotate it up and down, and notice it's working pretty well at hiding things that you can't see. You can also play games with the viewing. I shouldn't have that changed the clipping volume so it's not visible. I can change it a little more here. I can start decreasing and increasing the depth, and you'll see some clipping. But the main thing I want to show you is just playing around with this here. You can rotate it and notice that the mesh gets displayed beautifully. It folds up. It's being clipped over here, so you don't quite see the edges. But anyhow, that's what we get using polygon offset. So let me finish by just making a couple of comments about a little more mesh issues that we'll consider many of later. One is, what if you have a lot of data, which is point, and in some sense it's 2.5 dimensional, meaning that for every x and z value, there's exactly one y. This is what you would get, for example, if you did a laser scan. If you did a scan from, say, an airplane looking down at the Earth, you'd get exactly one height for every point you look down, but these data would be unstructured. You wouldn't have them nicely arranged in rows and columns in some matrix. There'd just be a whole bunch of data, literally tens of millions of points that are just XYZ points. So how do I make a surface out of that, say a triangular mesh out of that? That's a difficult problem, and we also want good triangles. We'll talk some more about that when we start talking about about lighting and shading in the next lectures, where what will happen is that long, thin triangles will look lousy when they're shaded, but you want things that look more like equilateral triangles. So in some sense, a Delaunay triangulation is optimal in that way. And how do you do that with lots and lots of points that are unstructured? You can also look at things like, can I take a mesh that's two-dimensional and display it as one long single triangle strip? That's kind of a cute problem. I think it's in an exercise in one of the back of, I guess, chapter 5 or chapter 4 of how you do that. And then there's sort of the inverse problem of given a mesh, how do you simplify that mesh? One of the things we'll see when we start talking about curves and surfaces is when you render a surface, you usually render that surface by breaking it up into a lot of little polygons, triangles. And what will happen is that you'll waste a lot of triangles in areas which are kind of flat. You know, if I have a flat area, like go back to that Honolulu data where you had the ocean, don't need very many polygons to represent large areas of the ocean, but then where things are changing rapidly, or measure of that is the curvature of the surface or the curvature of a curve, I would like to have a lot of polygons there. So how do I take a mesh that might have too many polygons in it and simplify that mesh? So these are a whole bunch of problems that come up with meshes that you know, a lot of them reside in the CAD community, but since you're going to be doing the graphics and trying to render these things, it'll really help to understand something about them. Okay, so that'll be it, at least for a while, about meshes.